Hi, I'm Leon Starr, and this is lesson 235 in my course, How to Specify Software in Complex Safety Critical Systems. With most modeling projects, it is easy to get started connecting a bunch of boxes and lines on a canvas. Sooner or later, though, the MBSE demons will stomp all over your pretty diagrams and make your life miserable. In this lesson, I'm going to show you how to build models that won't crumble to the ground when those demons pay you a visit. I'm going to put the spotlight on the changing requirements, complexity, and concurrence and synchronization demons. What they all have in common is that they lurk in the background, waiting for you to make some solid progress before they turn your work into a hellscape. Now, we're not actually going to slay these demons, but we can anticipate them and keep them chained up so that we can sustain productive progress rather than constantly backtracking. Let's start with this guy. We all know that change is inevitable when it comes to requirements, the target platform, everything. The changing requirements demon likes to wait until we've invested considerable effort in our models and then pop up with changes. We don't have time to start over or restructure all of our models at this point. So we hack, refactor, and throw in a miscellaneous element or two to house the unclassifiable odds and ends. This is a hot mess, and in this video, I'm going to show you how to organize your models at the very start so that you can avoid it. To succeed, we're going to need a smart strategy for mapping requirements to model elements. It's easy to see why if we examine a baseline dumb strategy. Let's say, for example, that we just directly map each feature in our requirements to some corresponding modeling element. This one-for-one correspondence will give us great traceability, but that's about it. Here are just three of the downsides. 1, by definition, each future change to the requirements would have a directly proportional impact on our model structure, so we have to rework the models with each and every change. 2, we know that a lot of requirements are just going to be cut and paste variations on the same theme. If the models are as bloated as the requirements, there isn't much point in building them. And 3, we want the models to direct the development of a well-designed software system that is itself resilient to change. The models can't do that if they simply mirror the written requirements. For the models to be useful, they should identify a smaller set of common building blocks that can be combined and modified to account for the whole set of requirements. But exactly what building blocks are we looking for? Functional building blocks are a common choice, and we get these through a functional decomposition strategy. The whole point of a software system is to do things, so why not focus on functionality as a basis for our model structure? Let's explore the strategy with our elevator case study. If you haven't watched part 2 of the introduction to my course, you might want to skim through the elevator intro linked here in the description. Here we sort through the requirements looking for functions that need to be performed. For example, we need a way to take a shaft out of service. We need to handle floor requests. That's where someone at a floor pushes an up or down button. We need to compute the average speed of moving cabins to decide which one might service a given floor request. We need to estimate the total transit duration of a potential transfer. And we need to handle cabin stop requests. That's when you push a numbered button inside the cabin to stop at a specific floor. We need to dispatch each cabin to one or more floors in a particular order, and so forth. We can keep listing these all day, right? Which brings us to our first challenge. How do we know when we're done? We have this assorted grab bag of functions, so how can we confidently say at some point that we've identified all of them? And even if we manage to do that, how likely is it that any future requirements will add even more functions or redefine what we already have? So completeness is an issue, but that leads us right into the second problem. As we model, we'll want to organize all these functions. Like maybe we'll draw a box called initialization and another called configuration, and maybe one called scheduling. And then we'll put boxes inside those boxes like dispatching, door controls, and so forth. We'll do our best to package it all up with the simplest interfaces up and down the hierarchy. But then we start discovering more functions as new requirements come along. Assuming we started out with a structure optimized for a set of known functions, each subsequent change potentially challenges the integrity of that initial structure. Eventually, some requirements change, or an accumulation of changes will manifest a significant disruption. When that happens, you can either refactor all or part of the structure. But as it grows in size and complexity, it will become more tempting to just pass along some flags that will result in switching logic down below. Or we just add a miscellaneous controller box here and there where we can toss in any new stuff that doesn't quite fit our pattern. So our initially optimal structure will begin to degrade immediately and in time, not so gracefully. Again and again, changes to requirements are going to threaten the integrity of any model centered on a functional structure. It's also troubling that any two modelers will almost always decompose a system differently. That's because the criteria for choosing a level or what content goes inside a given functional box is highly subjective. Instead, we would like an approach that gives us objective criteria so that we can converge on a single correct representation of the system we need to build. Convergence is a principle we'll revisit throughout the course. Okay, let's consider a different and less obvious strategy. Rather than organize our model structure around functions, we could build it around events instead. Here we sort through our requirements, identifying events that drive the activity in our system, such as a request to open the doors, arrival of a cabin at a destination floor, a going up or down call at some floor, a request to close the doors, and so on. Rounding out a complete list of events is easier than trying to guess all the required functions. You can then break down the functional components necessary to respond to each external event or to generate a response in the system's environment. Common functions and data can be identified so that the interfaces are simplified, and then you factor upward to get your functional structure. The end result looks similar to a functional decomposition since you still end up with a tree-like structure in the end. The difference is that you can make more informed decisions since you already have your low-level components in hand as you work your way upward. Contrast this with functional decomposition, where you start off with boxes of unknown content, and you're basically poking around in the dark as you descend and discover new details. So you end up refactoring on a case-by-case basis. The stimulus-response approach is a bit more objective, a bit more systematic. And since the event list is more likely to be complete, the resulting structure should be more stable. But in terms of stability, systematic partitioning, and a whole lot more, we can do better. A lot better. Both the function and event schemes are structured around dynamics, which, by their very nature, are subject to change. Assuming there is at least some overall agreement on what our system is supposed to do, surely there are some underlying principles that are unlikely to change much. In fact, there is certain foundational logic and an underlying vocabulary or semantics necessary to express that logic hidden in plain sight within the requirements of every system. Maybe these are the stable building blocks we've been looking for. For example, consider the rule that every shaft in our elevator system must physically intersect at least 2 floors, or that a cabin travels up and down a dedicated shaft. At any given time, a cabin is en route to at most one immediate destination, right? A cabin can't arrive at 2 floors simultaneously. These entities and rules in elevator systems haven't changed in decades. Think about that. I mean, that's geologic time in software terms. You can't get much more stability than that. Now imagine that 2 different modelers attack the same problem, and we do assume a common understanding of the domain in which they are modeling. These modelers should converge on the same model of semantics and logic. For example, you would expect to see door, cabin, shaft, transfer, floor, and their relevant constraints represented in either model. By the way, we use classes to model our semantics. Of course, 2 modelers are likely to choose some different names and geometric layouts here and there, but these kinds of decisions don't influence the executable logic of the models. It's the same in math, where the Pythagorean equation a squared plus b squared equals c squared is logically identical to x squared equals y squared plus z squared. In our case, one modeler might call a shaft-floor intersection a shaft level, while the other calls it a floor access point. Nonetheless, seemingly minor differences in the logical features of our models will specify entirely different systems. To quote the famous logician Wittgenstein, all logical differences are big differences. So by separating out the semantics and logic from the functions, those small logical differences are much easier to see and adjust early on. This all might be obvious for relationships among physical entities, but what about an abstract domain? Think about linear algebra. You would certainly expect any 2 modelers working in that subject matter to abstract a matrix class and a transformation relationship at the very least. I've modeled a lot of abstract domains in my career, and I can assure you that the same principles of stability and convergence for physical domains apply equally well to hypothetical domains. Class models are fine, but data and logic don't actually do anything. What about the behavior and the computations? We'll get there, but to make the most sustained progress as we model with the least backtracking, we want to proceed from the most stable elements to the most volatile. Since the semantics and logic are least likely to change, we want to model them first. The building blocks of this foundation are classes, relationships, and logical constraints. The next thing that is least likely to change are the overall behavior of each class and relationship. For example, doors open and close. A cabin arrives at a destination and is then dispatched to another. We model all this behavior with state machines that synchronize the life cycles of the relevant classes and relationships. Finally, state transitions will trigger various functions defined on the classes and relationships. We defer the definition of our functions as long as possible since they're most likely to be influenced by changes to our requirements. I can't stress enough how important it is to model in this order. There's nothing wrong, by the way, of doing this in agile increments, but each increment should proceed as described. Let's see how the structure absorbs a typical requirement change. Here comes a change telling us that we need to force the doors closed after 2 unsuccessful close attempts. Notice that this requirement does not present a challenge to our semantic foundation. We can satisfy it with existing classes and relationships. We will need a couple of new attributes, one to represent the current number of failed closings on any given door, and another to specify a maximum number of normal close attempts for all cabins in the same bank. And we'll need to update the life cycle of the door slightly, adding an extra state and action. But we won't need to do any refactoring. There's no challenge to our foundational semantics and logic. Assuming we do a good job defining our domain and class model, most new requirements will leave our foundational structure intact. So we can keep making forward progress without having to constantly refactor or hack our models to keep them working. So to deal with our requirements change daemon, we sift through our requirements, modeling the elements least likely to change. These are going to be the fundamental semantics and logic of our subject matter, and we capture these in a class model as classes, relationships, and constraints. In fact, we'll build a distinct class model for each domain in our system that we've decided to model. For example, semantics like cabin and shaft go in the elevator management domain, while motor, load, mass, and acceleration ramp go into the transport domain. So as you're filtering out details, you need to split them out to the appropriate subject matter domains. The class models define a stable, resilient, underlying model structure that won't be challenged much by most changes to the requirements. This sets us up for success as we layer on behavior and functionality. And that's why the focus of my course is on getting the class model built quickly and correctly for each model domain in our system. So much for the requirements change daemon, but what about those other two I introduced? How can our class models reduce the complexity of both data and behavior? And how are class building blocks superior to functions when it comes to specifying concurrency and synchronization? We'll get into all that in Lesson 236.